Welcome to Understand the Math. In this problem, we're going to diagonalize the following matrix A. To diagonalize a matrix, what we have to do is write the matrix as A is equal to P times D times P inverse. Sometimes you'll only be asked to find P and D, but if it's not specified, then you actually have to find P times D times P inverse. Our first step is going to be to find D. Our matrix D is a diagonal matrix that contains the eigenvalues of matrix A. Then we're going to find matrix P, and our matrix P contains the eigenvectors of matrix A. And then lastly, we'll just compute P inverse, and then we'll write all three of them side by side. Let's start by finding D. What we're going to have to do is find the eigenvalues of our matrix. So we have the formula to find eigenvalues, determinant A minus lambda I is equal to 0. We're going to take our matrix A and we're going to subtract lambda off the main diagonal. And we're going to set that equal to 0. This gives us a 5 minus lambda times a 3 minus lambda. We're just multiplying the main diagonal, and then we subtract off the off diagonal, which is 2 times 4 is 8, and we set that equal to 0. Multiplying this out, we're going to get a lambda squared. We have a minus 3 lambda minus 5 lambda plus 15 minus 8. Combining like terms, we get lambda squared minus 8 lambda, and then 15 minus 8 is a 7, so plus 7. Give us a little bit more space. We can then factor this. We have lambda minus 7 and lambda minus 1 is equal to 0. So that gives us our eigenvalues. Lambda is equal to 7 and 1. At this point, let's go ahead and write down our matrix D so we don't have to come back later and think about it again. So our matrix D is a diagonal matrix that contains the eigenvalues along the diagonal of D, and all the other entries are 0. So I'm going to put a 7 and a 1 along the diagonal, and then the other entries we're going to set equal to 0. Now let's go ahead and let's find P. So to find P for each lambda, we're going to have to find the eigenvector. I'm going to begin with lambda is equal to 7, just because I wrote that one first. And what we're going to do is we're going to take A minus lambda I, and we're going to augment it with 0, and we're going to have to put it all the way down in reduced echelon form. So let's see, our matrix A, we're going to have to look back up. 5, 4, 2, 3. So we're going to have a 5 minus 7, a 4, a 2, and then a 3 minus 7. And we have zeros. Let's see what this is equal to. This is going to be a minus 2, a 4, a 2, and then a minus 4. Oh, that's nice. Our second row is a multiple of our first row. So let me highlight that. That row is a multiple of our first row, so that row is going to go to 0. And then let's do some scaling on our first row. And let's take row 1, and let's replace it with row 1 divided by negative 2. And the reason we're going to do that is it's going to give us a 1 as our pivot. So we have a 1, a minus 2, and a 0. And then our bottom row goes to 0. We mark that as a 0. We can now solve for x1. That's our pivot variable. So we can say that x1 is equal to 2x2. And that tells us that our vector x, which is x1, x2, is equal to plugging in for x1, 2x2, and then x2. And we can pull out an x2, and that becomes our vector 2, 1. What we have to do now is pick a value for x2 so that we can find an eigenvector. I'm just going to let this be equal to 1 and make things really easy. So our eigenvector is going to be equal to 2, 1. We're going to have to put that in our pocket for a minute, and we'll come back to that after we find our other eigenvector. So now we're going to let lambda equal 1. And we're going to do a minus lambda I again. Let's go all the way back up here. 5, 4, 2, 3. So 5 minus 1 is 4. And then we have a 4, a 2, and then 3 minus 1 gives us a 2. And you can see that our second row is a multiple of our first row. And we can go ahead and scale our first row by 4. And we end up with 1, 1, 0, and then a row of zeros. Let's circle our pivot, and we can solve for x1. So we see that x1 is minus x2. So our vector x is equal to x1, x2. And then we'll plug in x1 is minus x2. And then we'll pull our x2 out, see if we can squish it in here, and we get minus 1, 1. Again, I'm just going to make things easy, and I'm going to choose this vector to be equal to 1. You could also have picked it to be minus 1. It doesn't really matter. And so our eigenvector is going to be minus 1, 1. Now we can go ahead and write down our P matrix. So the only thing that we have to be really careful about is, let's go back up to D. Do you see that 7 is in our first column? So that means the eigenvector corresponding to our eigenvalue of 7 also has to be in the first column. So that's this one right here, and we have to put that in our first column. So 2, 1, and then the other one goes in our second column. Now our third step is to find P inverse. So P inverse is going to be 1 divided by the determinant of P, which is the main diagonal 2 minus the off diagonal, which is negative 1. And then inside, our main diagonal entries switch, and our off diagonal entries get a negative. So notice that this is equal to 3. So every entry is going to be divided by 3. We can now write down our final answer. So our final answer is matrix A is equal to our matrix P, 2 minus 1, 1, 1, times our matrix D, which was 7, 0, 0, 1, times our P inverse, which we just found to be 1/3, 1/3, minus 1/3, and 2/3.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.